In this video, I'm going to explain onset detection, show you the various algorithms for detecting onsets and how to fine-tune them. But first, what is an onset? An onset is the start of a sound event in an audio signal.
So before we even get into Max, it's important to consider your input source. Using something like an Omni microphone is good for getting the sound of an instrument within the context of its space, but for onset detection it isn't ideal because it's hard to isolate the sound from the room. A cardioid mic does a better job of this, but still picks up too much of the space for optimized onset detection. Something like a hypercardioid is a good choice, as you get really good isolation and directionality. Ultimately, you'll get the best results from something that is instrument specific. So something like a sensor percussion sensor or drum trigger or similar, that'll give you a really focused sound from the source that you're trying to pick up. And failing that, a contact mic is always a good option for attaching directly to an instrument. So here we are inside Max. Now I've got DK Onset here, which is the basic onset detector, and we're going to take a look at the outputs from it. So the leftmost output reports a bang. That's useful for like playing back samples or triggering MIDI notes, things like that. Then we have two signal outputs. We have a trigger and a gate, and this is what they look like. So depending on what you need, you can just take the bang if that's useful for what you're doing. But if you want the lowest latency possible, you want to use the trigger output and then do your processing down the line based on that. The difference between trigger and gate is that gate will give you a gate length based on the amount of time that the signal has passed the threshold. So if you look quite closely, you'll see that the gate kind of gives you some length, whereas trigger is a single sample spike. So it reports like super quickly. Gate gives you a little bit of duration. It doesn't give you note length duration. It's not really that kind of thing, but it does give you some idea of how long the transient was. So we have three main types of onset detection algorithms in data. We have DK onset, which is for amplitude-based onset detection, spectral onset, which is spectral onset detection, and novelty, which computes novelty on various different metrics that you can load into it. In general, DK onset is the fastest since it's time-based. Spectral onset will be a bit slower, but will let you focus on different aspects of the sound. And novelty can not necessarily, but tends to be a bit slower than that because of the way it computes things. So the way I like to think about it is DK onset is good for immediate fast things where you have changes in volume. So things with percussive sounds or clear attacks. Spectral onset is where you have differences in sort of timbre or pitch or things like that where the amplitude doesn't necessarily change over the period of time. And then novelty is generally good for things that change maybe more structurally. Like you can use it to detect shorter time frames, but it's more oriented around computing novelty across slightly larger time frames. So across all three algorithms, we have sensitivity and lockout as our general parameters. So sensitivity will, if you increase it, you will have a higher sensitivity. Decrease it, you have a lower sensitivity. And then lockout will be how soon onset can be detected again. So here I have it quite conservative at 200. So if I just send some audio into here, you can see what gets caught by the various different algorithms. So they each have their own strengths and weaknesses. You can learn more about the different algorithms in the help files for each, as well as looking at the Flucoma Learn pages for each of the underlying algorithms. So in terms of fine-tuning things, I'm going to demonstrate here with the amplitude-based approach, but you can use a similar workflow for optimizing and tweaking the other onset detection algorithms. So I have some audio here of a gong drum. I'll just play a bit of this and explain what we're looking at. So the yellow line that we see at the bottom is not the direct audio that's being measured. The yellow line represents the differential between two envelopes. I'll explain this in a bit more detail when I explain how the algorithm works from scratch, but basically it's the difference in amplitude from moment to moment. The green line represents the threshold at which it needs to pass before an onset is detected. The red line represents the lower threshold that the signal needs to cross below before it can re-trigger again. So again, if I just play a bit of audio, we can see the differential there. We can see that it's passing the threshold, it's triggering an onset, and then it needs to go below that red line again. When I'm tweaking things, the first thing I'm going to look at is these macro parameters. The sensitivity and lockout, as we saw from the previous tab, are the same across all the algorithms. But here for the amplitude-based approach, we also have a floor. So the sensitivity, if I turn it up, you'll see both lines move. So I brought the top threshold down and the bottom threshold up. This means the signal will more likely pass the upper threshold and then also pass the lower threshold. If I bring this all the way down, you can see it will be harder for the signal to pass the green line and then the red line. So I'll just play some of the audio and adjust this here so you can see the difference. So my first place is just the sensitivity. Now I can adjust that up and down, and that'll give me an overall macro sense of making it more sensitive or less sensitive. The lockout will affect how soon an onset can re-trigger again. So for things where you expect to play quickly, so percussive stuff or very fast runs, having something small like this at 30 milliseconds, which is the default, is pretty fast. I can put this a little bit higher, so if you're not playing very fast, you might want this a bit here, so you don't get so many like accidental re-triggerings. So if I put this about 150, you see it's missing some of the faster runs there, so depending on the kind of material, that would matter more. So floor is the threshold below which nothing will get triggered at all. Now here I have digital silence going into it, so we don't see anything moving. But if you had a microphone plugged in, you would see this kind of dancing down here at the bottom. So if I play some audio here, and if I adjust the floor, you see some of the signal gets absorbed. So nothing below negative 27 dB is even just registering at all, which impacts the sensitivity. So if I bring this down some, you can see that only like the really clear peaks come through. And if I bring it all the way down, everything comes through. And we can see kind of a bit of the noise floor of the signal dancing there. If I put it back to 70, the default, you can see the bottom end gets smoothed out a little bit. So in terms of fine tuning things, you can see I have the 1, 2, 3 here that I'll adjust. So first thing I'll adjust the lockout based on how quickly I plan on playing. There's no visualization for what that means here, but if I know I'm going to be playing fast, I might leave it at the default. If I know if I'm playing an instrument that's going to be a bit slower, I might turn this up to 100 as a good safe point for a lot of playing. Then after that, I'll adjust the floor. So here I have digital silence going in, so there's nothing happening. But if I had a microphone plugged in, I would adjust this floor parameter to where basically it just tickles and you see a little bit of dancing at the bottom. So somewhere between negative 70 and negative 50 is usually where I end up setting it. And that'll give me a good baseline where things that are below that will just get completely ignored. And then after that, I'll adjust the sensitivity to taste or to what I need. There's some additional parameters here for advanced settings, but I'll explain those a little bit later in the video. Up next, we have different input modes. So the input modes help you optimize things depending on the type of microphone input that you have. So if you have a normal air microphone, you'll just leave it at the default, which is input 0. If you have something like a sensor percussion sensor or a 3D printed one, you can use input 1. And then finally input 2 if you have something like a contact mic or a drum trigger or something along those lines. What this does, it will apply an EQ that helps the onset detection algorithm work a little bit better. And here you can see a rough explanation of what that is, but I'll play an example here where this left one, both of them have the sensitivity set to 60. This left one here is set to input 0, so a default air microphone. And on the right here is set to input 1, which is for sensor percussion. And you can look here at the bottom to see how many more onsets the one on the right gets. You can see all those press rolls still come through. So now I'm going to explain how this is built from scratch. So if I'm going to build an onset detector from scratch, I'm going to show how to do it from a basic version, one that's slightly improved, one slightly improved, and then how to actually do the version that we have in Datanaught. So at a basic level, we have the raw signal coming in. Okay, then one of the first things I want to do is I want to rectify the signal. So that means it's just from 0 and above. So anything that's a negative value gets turned into a positive value. And we have this here. Now after that, I want to smooth it a little bit. So here I have slide with a fast up and a slower down. And that gives me kind of like sort of an envelope follower type thing. So the yellow signal that you see here is that envelope follower. And now with the threshold here, I can adjust this and this will basically do a very, very basic onset detector. It's kind of fickle here in that you can see that near 0 is a value that I need, but if I put this to like this, it'll never trigger. So even though these values are teeny tiny, it's quite hard to tune within this little window. All right. And then at the bottom here, there's just a little bit of logic. So if the signal is greater than whatever I set my threshold to, it'll trigger. So I can see that there. Now in this case, I don't necessarily want the whole gate signal, so you can see that. So I'm getting a change, which gives me a signal spike up when it goes above the threshold, and then one when it goes below. And then I'll clip it so I ignore the bottom one. And then this effect gives me a signal trigger here, and this will be the gate signal that I get from DK onset. Now, if I want to improve this a little bit, the first thing I want to do is improve this thresholding here. So rather than doing this with the amplitude-based thresholding, I want to convert to dB. So here I have the same type of thing, but I'm going to be doing dB scaling. So if I play this, I have the rectification just like before. I'm converting it to dB. I have slide just like before, and here I have the same envelope follower, but now in a log scale. Now this is much easier to take a threshold of. So I can put this here. I get the gates, I get the sort of change, and then finally the onsets at the bottom. So this works a lot better, but the main issue with this is if I get near the point of change here, kind of around there, you can see I start getting all these wild triggerings because there's nothing to say, there's no hysteresis, so nothing to say that the signal's gone above and then below a different number. So that means if you're near the threshold, you get these wild clusters of onsets that aren't really representative of what's actually happening. So in order to improve that, we want to add a hysteresis. So we've got the same as before, rectification, convert to dB, the envelope follower. And now the difference here, rather than taking an absolute threshold, so if it's above a certain value, I'm using thresh here. So this gives me two values. So the low threshold and then the high threshold. So if I turn this on, I see I have now two values. So if I get this kind of a bit lower to the bottom there and bring this down, you can see I don't get that wild set of clustering that I did before because the signal needs to go above the green one and then below the red one in order to trigger. So here we have a deconstructed version of what's inside DK onset. So at the beginning we have a filter. So there's a pre-filter before the rectification. And in this case, it's set to a pretty high frequency. So we're ignoring a lot of the low frequency energy because we're focused mainly on the transients. So this is the default settings that you have in DK onset when you load it up. We have a 2K high pass filter. So only frequencies above 2K will go through, which is really, really high. Rectification. Then we have the conversion to decibels. And then here's where the floor comes in. So this sets the maximum value and anything below that gets cut off. Then after that, we have two envelopes. So this is where the algorithm really bifurcates from this from scratch version here. Rather than just taking the raw envelope follower, what we're doing is computing a differential. So I'll show what this means. Okay, so if I stop the audio, we can look here. So what we have is a couple different things here. So we've got this blue one, which represents the fast envelope follower, which is this slide here. Then we have the red one, which is a slow envelope follower, which is this one here. And then we have the yellow line that we were looking at before. This is the difference between the two. What this is good for is basically giving you a relative threshold. So rather than being an absolute threshold where is if the signal goes above that point, full stop. So whether I'm playing loudly or quietly, it doesn't matter. It's this specific decibel that needs to be passed. By having this differential approach, that moves up and down, meaning that if I'm playing quieter or if I'm playing louder, the difference between the signal of now to just now is what will trigger the onset. So this yellow line here is what the threshold is being computed on. All right, so I'll play a bit more audio. Okay, so here I've got some fast hits. So I can see that this triggered, and this triggered. I missed that peak there. You have to kind of use your judgment whether you consider that to be an onset or not. But you can see the slow envelope is moving around. The fast envelope, which is the blue one, is kind of dancing up and down with it. And the difference, which is this yellow one, we really get at these clear spikes. So that represents this section here, the volume differential. Then after that, here we have the sensitivity. And then finally the lockout, which is the other difference from this from scratch version that we've done. So in the version that I built here, there's nothing to say that something can't trigger again because I'm just measuring the signal directly. So here we get all the basic onset detection that we get from this section, but with the bells and whistles of having the floor, the differential, and then finally the lockout. So if we go into advanced tuning now, there's more that we can do to really extract out of this. So we can use the microparameters as we were doing before. And with that, we can do most of what we need to do. So I'd say about 90% of the time, I just use these macro parameters when I'm tweaking the onset detection. But sometimes for certain signals, I need to go into here. So I'll explain what these do. So I move the sensitivity up and down here. I can see that the green line and the red line move independently. Those lines correspond to the on threshold, which is this one here, and the off threshold respectively. So if I wanted to, I can adjust the sensitivity as I want, but I can also independently set these values. So if I want to have this to be about there, I want to bring this to there, I can set these as attributes for decay onset and have that be a bit more fine-tuned, or I can set the sensitivity. It's kind of an either or. So that's one of the first things that you can do, manually set your on and off thresholds. Now, another thing you can mess with is the high pass frequency. Now here it's set to 2K, which is pretty high considering the type of audio that you might want to send into this. I found with a lot of experimenting and sending a lot of different kinds of audio, having a high pass frequency here actually helps the onset detection regardless of the instrument. So even if you're playing a bass or a tuba or a kick drum, having a high pass frequency like this really still captures everything. But if you wanted to, if you bring this value down, this will let more low signal through. And just to kind of show as an example, so if I bring this down to, let's say, like 200, okay, and I'll run this audio, I'll put everything back to default here, and I'll run this audio from the beginning, and let's see what we get. So there's a lot more stuff going on. So the transients with this particular audio all still get detected, but there's a lot more low frequency energy, which for some percussive stuff could just be almost like DC signal. We have like low pressure waves that are moving through it. So you can tweak there. What I've actually found more useful is for certain kinds of signals, having this be much higher. So let's say like 8K, which seems crazy because there's not a lot of audio that you would think would be above that, but it actually works quite well. So here's the same drum signal, but with 8K. You can see you get more of just those peaks. So I'll kind of put this to, let's say 80, and I'll play this. I'll just kind of loop this first section here. So you see all this like low frequency information, all this like wobble in the signal. And here we have just the transients that are a bit more focused. So if anything, I find putting this signal up can be beneficial, but the default of 2000 here I find works pretty well. Now after that, we have the actual envelope follower times. So that we have the fast ramp up, fast ramp down, and then slow ramp up and slow ramp down. These start getting really esoteric and sort of experiment at your peril here. But what we have here is the slow up and down time. I tend to send at the same value, but this is the kind of rate of time at which you want to measure. So if I play some stuff here, that represents, in this case, the red line. So the kind of trend of audio. So if you're playing perhaps some more, not necessarily slow material, but material that has slower responding transients, you can put this a bit higher, maybe, 5,000 or something like that. You don't necessarily want to go crazy high with this, but if I put this at a bigger window, this will be the larger scale of time that's getting measured for difference. So if I run this again, but with 5K there, and let's go even crazier. Let's put this at 10,000. So that's sort of roughly a quarter of a second. We actually don't see a massive difference, but you can see here the red line is moving. It takes a lot more energy for the red line to move up before it moves back down. So I'll put this back to 5,000 just to have a different point there. Now the bigger difference will come in the fast ramp up and down. So with these values here, clear that. With these values here, this is how quickly it will separate itself from this. So 3 samples will make for very, very low latency, but it means it's very, very kind of nervous and triggery. So if you find that this is responding too quickly, you can make this a bigger value, let's say 50 or something like that. And there has to be a difference of sort of the signal at 50 samples to 5,000 samples. And that's where we're looking at our detrending. And similarly, this is the downtime. As I said, this starts getting a little bit weirder here in terms of messing with these values, but roughly this represents the window of time that we're looking at. And then this represents how quickly it will respond. and then how quickly it will release. So if we're thinking of a kind of compressor, this would be your attack and your release in a compressor, if you're used to that way of thinking. But for the most part, I find that either the sensitivity or the on and off threshold specifically on its own, then I'll look at the high pass frequency, generally speaking, moving it up if I need to. And then as a last resort, I'll mess with these values. And then you have to kind of go back because based on what you adjusted here, all of these will change as well. So that explains a bit of the advanced tuning. So one of the things I didn't explain is this different envelope mode here. So what this will do is it will take the dB signal that we have as the output and linearize it again if you want. So we have an option between logarithmic, which is the default, or linear. Now this I found most useful for signals that have a lot of loud sustain. So in this case, I'm using a cymbal. I found that I was having a hard time getting, let's say like fast ride pattern on a jazz cymbal going. The roar of the cymbal made for a much more difficult signal to try to extract onsets from. So with a default logarithmic envelope, we get this. So this signal on the left here. So you can see I'm missing a lot of like the dun, 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 all of the individual hits are getting missed. If I switch over to the linear version, so all of this is doing is taking the envelope, re-linearizing it, so it's getting converted to dB, and now I'm converting it back before the thresholding. And what that does, it gives me these clearer spikes. And to show you what that looks like, so if I come over here, I'll put everything back to default just to make things easy. So this back to here, this back to here, and this I believe was there. Okay. All right, and if I play some audio into it, and if I change this to linear, you can see the difference are much spikier. So it separates the peaks from the base signal a bit more. In general, I still use logarithmic as my core thing. I only switch over to linear if I have to, but you do get a different set of thresholds, and then your on and off thresholds, you have to adjust correspondingly. The sensitivity macro parameter is adjusted such that 50% will have different values for linear and logarithmic. So that's by design. So you can still have a sense of like, I want this to be 75% sensitive. You can switch over and the values will be where they should be based on a bunch of testing. But that's the envelope modes. And then finally, to show some examples of how you can use onsets within data now. You can use this in a bunch of different ways, but just to give you a quick example. So here I'm using the signal to trigger samples. So every time there's an onset, it's triggering a new sample. So here I'm using the gate output. So we have a variable gate length, and I'm using that to trigger an ADSR. Here I'm using triggers to trigger a Karplus strong algorithm. And because the onset detection happens so quickly, you can even do things like onset-based processing. So here I have DK Sift, which is basically an onset-based audio sifter. So by default, it's setting 50% of the onsets will go through. Or I can set it to be like every third onset will go through. And because it responds so quickly, you can basically do this in real time. So you can have only some of the hits go through, and then the other hits will go out to another output, and you can use that for interesting processing. And on a similar note, I'm using DK Scatter here, which will send audio to a different output, in this case using a multi-channel cable. So basically you almost have like a bunch of guitar pedals in parallel. So as opposed to in series, like different effects, and every time there's an onset, it will move from one to another. And finally here I'm using the trigger output to sample accurately trigger samples in a way that it lines up directly with the audio. So there you go. That's an overview of onset detection within data knot.